Let's consider the following problem. Consider a parallel plate capacitor as being charged with a current I. If the capacitance is C, what is the potential difference as a function of time? B, what is the electric field as a function of time? The capacitor has area A and separation D. C, compute the change in flux d phi E dt. All right, so this is very important to start with a picture here. So let's draw a picture here. So let's imagine a parallel plate capacitor. Oh, I need a new pen. All right, let's consider a parallel plate capacitor here. Okay, now this one is going to have a separation D, okay, and there's going to be area A. And between these two things, there's going to be some electric field, right? And I'm going to charge this up with some current I flowing into it. And so as a result, I'm going to build up Q on this side and minus Q on this side, all right? So let's first figure out basically what the potential difference. So the potential difference, V, is equal to Q over C. Okay, so you need to find what Q is. Well, we just note I is equal to dQ dt, right? And being charged with current I, that means that Q is going to be the integral of I dt, which for I is constant, is going to be something like I times t. All right, now there's always a integration constant. We're going to ignore that for now because that's not going to be important. All right, so it can be I times t over C. All right, so that's basically part A. Okay, so that's going to be something like this. You could actually add an additional thing, but that's not going to be relevant for the purposes of this computation. B, what is the electric field as a function of time? The capacitance A and separation D. Well, for part B, we're going to note that the potential drop is just going from 1 to 2 of the electric field dot dl, right? Okay. And let me try to think what's the best way of doing this. Technically, it's a minus sign, and we're going from basically plate 1 to plate 2, all right? And so this is just going to be basically be E, some constant electric field, times the integral of dl. Well, what is that? That's just going to be E times d. Now, let's get the sign right. So this is going to be going down. So we're going to make this a plus sign. All right, E times d. Okay, so that's the potential drop now. All right. And so what I want to figure out is basically what the electric field is. Well, that's easy enough to figure out. E is just going to be V over D, all right? And then it's going to be pointing upward, right? So that's basically part 2, okay? Now, let's compute the change in flux, C, okay? The change in flux, all right, phi E is just basically integral of E dot dA, okay? And the area is just this. So you note the area, the normal vector is parallel to the electric field. Okay, so in this case, and electric field is constant, so it's just simply going to be E times dA, right? Which is going to be basically E times A. All right, so that's basically the flux, and so to compute basically d phi E dt. Okay, if you want to make this a little more complete, it might be helpful to include this term on the top. IT over DC, all right, okay, and this is just going to be equal to, let's see, that's going to be equal to dE dt times A. A is constant, so we don't have to worry about that. Well, the dA dt, and so if we basically compute this thing out, let's plug this in, so it's d by dt, all right, there's A out front, IT over DC, and the only thing that corresponds to T is this T right there. That's basically AI over DC, right? And so those are the 3 answers that we need.